This is the lecture number 4 for the chapter Principle of Mathematical Induction, and we are discussing the exercise 4.1 and we are doing today question number 11. As usual, we'll do it. Let this statement will be equal to Pn, which is equal to 1 upon 1 into 2 into 3 plus 1 upon 2 into 3 into 4 up to 1 upon n plus 1 n plus 2 is equal to n plus 3 upon 4 n plus 1 n plus 2. So for n is equal to 1, the left hand side will be 1 upon 1 into 2 into 3, which is equal to 1 upon 6. In the right hand side, 1 into 1 plus 3 upon 4, 1 into plus 1, 1 plus 2, which is equal to 1 upon 6. So left hand side is equal to right hand side. So it is true for n is equal to 1. Let this statement is true for n is equal to m. So we have to replace simply n by m plus 1, m plus 1, m plus 2 in the left hand side, m plus 3 upon 4 m plus 1 m plus 2 in the right hand side. So in the we have let that it is true for n is equal to m. Now as usual, we have to add the next term of this, which is 1 upon m plus 1, m plus 2, m plus 3 on both sides. You have to add the next term of this to the left hand side and to the right hand side, because we have to prove that it is true for the m plus 1. So in the right hand side, we have added the next term, and on simplifying the right hand side, you should obtain the next term of this, which is m plus 1, m plus 4 upon m plus 2 into m plus 3 in the right hand side. So you simplify it, you are getting common 1 upon m plus 1, m plus 2 common, and you are getting m plus 3 upon 4 here and this, and you are getting this. And to factorize this numerator by splitting by factor theorem, and on factorizing the numerator you will get m plus 1, m plus 4, m plus 1. In the denominator we have 4, m plus 1, m plus 2, m plus 3, and in this m plus 1 will be cancelled out, and you are getting m plus 1, m plus 4 upon 4, m plus 2, m plus 3, which is the next term of this m plus 1, m plus 4 upon m plus 2, m plus 3. This factorization, you can't do it directly, you have to do it somewhere in the rough column to obtain the factorization of this. So in the end, as usual, we write that this is true for all natural number by PMI whenever it is true for n is equal to m. So this is the question number 11. Now in question number 12, you have to prove that this statement is equal to a r raised to power n minus 1 upon r minus 1. In the left hand side, we have ar square up to a r raised to power n minus 1. Let the statement be equal to Pn. For n is equal to 1, the left hand side is equal to 1, and then right hand side replace n by 1. So r minus 1 upon r minus 1, you are getting a. So left hand side is equal to right hand side, which is equal to same. So we let that it is true for n is equal to m, replace n by m in the left and the right, and you have to add the next term of this, which is equal to a r raised to power m plus 1 minus 1, which is the next term. Add left hand side as well as in the right hand side, and on adding these two terms you should obtain a r raised to power m plus 1 minus 1 upon r minus 1, which is the next term for this when it is true for m. Then to be true for m is equal to m plus 1, you should obtain in place of m plus 1 in whenever we have m. So simplify this, and once 1 cancelled out, adding by taking the LCM r minus 1, and open the bracket, a r raised to power m minus a r raised to power m plus 1 minus r raised to power m, open the bracket. This term will be cancelled out, take a common here, so a minus r raised to power m plus 1 should be here, it should be m plus 1. So taking a common, r raised to power m plus 1 minus 1 upon r minus 1, which is the next term of this. So it means it is true for n is equal to m plus 1 whenever it is true for m is equal to m. Therefore by PMI it is true for all natural number. In question number 13, see it very carefully. In place of plus, we have the multiplication of the terms. See it very carefully. Product of these terms is equal to n plus 1 ka whole square. This is the statement here. So let it equal to Pn. For n is equal to 1, the left hand side is 1 plus 3, that is 4. In right hand side, replace n by 1. So 1 plus 1 to whole square, it will be equal to 4. So left hand side equal to 4, right hand side equal to 4. It means it is true for n is equal to 1. Now let us true for that it is true for n is equal to m. So simply you have to replace m by n here as well as here. Here. And in place of adding, you have to multiply both sides by the next term of this. See the next term of this very carefully, and the multiply we have to do, because in the previous questions, in all the questions we have added the terms, because the terms were added. Here the terms are multiplying, and the product of these terms is equal to this. So multiply the next term of this, which is 1 to m plus 1 upon m plus 1 ka whole square in the left hand side as well as in the right hand side. So see it very carefully. Multiplying both sides. This and in this. Multiply both sides. Yes. Now simplify the numerator. I am getting this. Whole squaring and adding, I am getting this. M plus 1 whole square will be cancelled out, and this is m square 4m plus 4, which is the whole square of n plus 2, which is the next term of this, that is m plus 2 whole square, like this. So by PMI it is true for all natural number, and Pm plus 1 is true whenever it is true for n is equal to n. Similarly is the question number 14. The product of the terms are given, whose product is equal to m plus 1. For let it is equal to Pn. For n is equal to 1, left hand side will be 1 plus 1, which is 2. In the right hand side, replace n by 1, which is also equal to 2. So left or right equal, therefore it is true for natural number 1. So let for true Pm is true, that it is true for n is equal to m. So replace n by m in the left hand side, in the right hand side as usual. Now multiply, you have to do it again because the terms are being multiplied and the product is m plus 1. The next term of this will be 1 plus 1 upon m plus 1. Multiply both sides by this in the right hand side also. This. Simplify this. You are getting this. M plus 1 cancel out. M plus 2, which is the next term of this. So it is true for n is equal to m plus 1 whenever it is true for n is equal to m. Therefore, it is true for all natural number by PMI. Now in question number 15, we have 1 square plus 3 square plus 5 square up to 2n minus 1 ka whole square equal to 2n. 2n minus 1, 2n plus 1 upon 3. This is the sum of the n terms. For n is equal to 1, as usually let this is equal to Pn. N is equal to 1. The left hand side is equal to 1 square, which is equal to 1. Replace n by 1 in the right hand side. 1, 1, 1 upon 3. You are getting 2. Left or right both equal. Therefore, it is true for n is equal to 1. And let it is true for any natural number m. 1 square, 3 square up to 5. Replace n by m. 2m minus 1 whole square in the right hand side. Adding the next term of this, which is 2m plus 1 minus 1 whole square. Adding the next term to this as well as to this in the right hand side. Yes. Simplify this. You will get the next term of this will be m plus 1. See it very carefully. 2m plus 1 minus 1. 2m plus 1 upon 3. This. Add it. The calculation part somewhat lengthy in the right hand side. Adding by taking the LCM, so 3 will be there. Simplify this, it will be 2m plus 1 whole squaring and multiplying by 3. We are getting this, and taking 3 common, it is equal to this, and the factor of this will be 2m plus 1, 2m plus 1, because 2m plus 1 whole square will be there. You can take common 2m plus 1 common in these two terms. Common here, so m 2m minus 1 will be here, 3 2m plus 1 will be here, and if we open this bracket and factorizing, you are getting this. Open the bracket, second bracket, and factorizing, you will get this. M plus 1 to m plus 3 upon 3. Now for m plus 2m plus 3, you can m plus 1 as it is. For 2m plus 1, you can write 2m plus 1 minus 1. For 2m plus 1 plus 3, you can write 2m plus 1 plus 1. This is equal to this is equal to this, and this is equal to this. Simply you have to arrange, because you have to show that this is the next term of this, which is m plus 1, 2m plus 1 minus 1, 2m plus 1 plus 1. You have to prove that this is the next term of this. You simply have to see the arrangements and show that it is the next term of the right hand side for Pm. So therefore it is true for n is equal to m plus 1 whenever it is true for n is equal to m. Therefore by PMI it is true for all natural numbers. In question number 16, again in the right hand side some calculation part is there, more calculation part is there. So let Pn is equal to this statement, which is equal to n upon 2n plus 3n plus 1. For n is equal to 1, the left hand side is equal to 1 upon 4. The right hand side will be 1 upon 3 into 1 plus 1, which is equal to 1 upon 4. So left hand side is equal to right hand side. So therefore it is true for n is equal to 1. So let it is true for n is equal to m. Replace n by m in the left and right. Here, adding the next term of this, see it very carefully. What is the next term? It will be 3m plus 1 minus 2, 3m plus 1 plus 1. See the next term of this. 3m plus 1 minus 2, 3m plus 1 plus 1. Adding this to the left as well as right. Here, open these brackets. Simplify this. You are getting 1 upon 3m plus 1 common, m, 1 upon 3m plus 4. Adding these two terms, which is getting 3m square plus 4m plus 1. And factorizing it by splitting the middle term, it will be m plus 1, 3m plus 1, factorizing the middle term, 3m plus 4 in the denominator, 3m plus 1 in the denominator. And which term being cancelled out? 3m plus 1 is cancelled out with 3m plus 1. We are getting m plus 1 upon 3m plus 4. And 3m plus 4, you can write 3m plus 1 plus 1. You open this bracket, you will get this, because you have to show that this is the next term of this, which is m plus 1 upon 3m plus 1 plus 1. 3m plus 1 plus 1. So it is true, which is the next term for Pm. So by PMI it is true for all natural number, and Pm plus 1 is true whenever it is true for n is equal to m. We'll discuss the remaining question in the next lecture. Thank you.